So one part of axial members, and in reality all the different types of loading that we look at, one aspect that often gives students a lot of problems is plotting out the internal loads across the length of the member. So in chapter 4, when we're talking about axial members, we're concerned with the internal normal force, capital N. When we look at torsional members, it'll be the internal loading, the torque, capital T. When we look at beams, we care about the internal shear, capital V, and the internal bending moment, which is capital M. And often we're going to try to plot out those internal loads across the length of the member that we're looking at. It's a good way to get an idea of what's happening internally, and it'll often give you an idea about which regions of the member are canceling each other out in terms of deflections. So it's important to be able to go from an external loading, which you see on these 4 different examples here, and calculate the internal resultants due to this external loading. Because again, in all of our calculations for stress or for deflection, what we care about are the internal loadings. The only reason that we care about the external loadings is because from the external loadings we get to the internal loadings. So capital N, V, M, and T, those are all internal loadings that we care about, and we just use the external loadings to get there. So I want to go through 4 different examples here of 4 different types of external axial loads that you might encounter, and then we're going to walk through how to get to the internal normal force that is caused by the external loads. And so the first type of loading that I want to look at is a horizontal column, and it's subject to 4 different applications of axial load. We have 6 kips here at this point, 2 2-kip external forces at this next point, 2 8-kip forces at the next point, and then 6 kips again at the end. These are all in different directions, and we can see if we were to do the summation of all the forces in the horizontal direction, we'd find out that this is in static equilibrium, which is kind of step number 1 to verify that. So going to the left, I have 6 kips plus 2 is 10 kips, plus 6 kips, I have 16 kips total pointing to the left, and I have 2 8-kip forces pointing to the right, which is 16 kips. So they cancel each other out. The sum of our forces in the horizontal direction here is 0, which is a good thing to check starting out. But again, we don't necessarily care in terms of analysis what the external loads are. For all of our strength and materials calculations, we care about what the internal loads are. And for axial members, that's going to be the internal normal force. So we want to plot out for this member with discrete loads how the normal force, what it looks like going across the length of the member. So the way that we do that to go from external loads to internal loads is straightforward. It's the same as what we did in statics. We're going to make section cuts between each of these points of discrete load application, and we'll make a free body diagram. We'll solve for what the internal normal force is. So again, at this point it's still just statics, and so all that we need to do is draw a free body diagram. So for this first section cut, we'll call it section cut 1. And for all of these free body diagrams, I'm going to use the same coordinate system. Y is positive going up, X is positive going to the right. My first free body diagram for this first section cut, I'm going to keep the portion of this column to the left of the section cut. So there is that. Here's my section cut. And to draw these normal force diagrams correctly, you have to follow the sign convention. So again, remember, this coordinate system is not the sign convention. This coordinate system is just a way that when we sum up the forces in a direction, this just tells us when we're summing them up which values are positive, which values are negative. The final answer, the internal normal force, will not be changed by which direction your coordinate system is pointed. What will change your answer for the internal normal force is which way you draw your assumed direction of the internal normal force. So again, for axial members, for internal normal force, our sign convention is that we assume positive is tension. So we always draw a tension vector for the internal normal force. Even though we might know it's going to go the opposite direction, you always just draw it assuming tension. So that means that we're pointed away from the section cut from the member that remains after we make the section cut. So here's this first internal normal force, and the only other thing that I'm missing from my free body diagram right now is any external forces that are left over after I make my section cut. So I've made my section cut here. Everything to the right goes away and it's replaced by this internal normal force. Everything to the left remains. So here my 6 kips pointed to the left, that's going to stay on my free body diagram. And so now all that I have to do for this section cut is sum the forces in the x direction equal to 0. And again, this 6 kips is pointed to the left, so that's negative 6 kips plus this internal normal force for section 1 is equal to 0. In other words, the normal force in section 1 is equal to positive 6 kips. So I can draw in positive 6 kips right here for this first section. This is positive 6, okay? It doesn't change between the far left side of the column and this first point because there's no intervening axial forces in between those 2 points. So it has to remain constant. Okay, section cut number 2. Again, anytime that I make a section cut, I can choose to keep either the portion of the assembly to the left or to the right of the section cut. Here I'm going to keep the portion to the left. And so my free body diagram for this second section cut, I'll have a little bit more of this column. I'll have my section cut, and I'm going to draw my assumed direction of my internal force acting on this second section cut, and I'll have my external forces as well. Actually, I kind of forgot to draw this portion a little bit wider. It's not going to affect the result, but just to make it consistent with my diagram up there, it gets a little bit wider. And so we still have our 6 kips pointed to the left, and then where it gets wider, where it bulges out, I get two kip axial forces applied here. All right, now when I sum my forces in the x direction equal to 0, I will get minus 6 kips, minus 2 kips, minus 2 kips because both of these are pointed to the left. So minus 2 times 2 kips, which is just 4 kips, plus the normal force in section 2 is equal to 0. So minus 6 minus 4 is negative 10. I move that to the other side as positive 10. And I get that the normal force in section 2 is equal to positive 10 kips. So I can draw that on my diagram now. I jump up, and it's a constant 10 kips from this point to this point because there's no external forces applied in between. All right, so we have a constant value between those 2 points. Okay, and we just have one more section cut to make. That's section cut number 3 here. And again, I can choose to either keep everything to the left or keep everything to the right. In this case, in terms of math, it's going to be easier to just keep this small section to the right. So my free body diagram will just be a short little section. On the right, we have our section cut. And I'm going to draw my internal normal force for this third section cut pointed away from the section cut. Or in other words, we're assuming positive intention. This is the normal force in section 3. And the only other thing that I'm missing from my free body diagram is this external 6 kips. And that's pointed to the left. Okay. Sum the forces in the x direction equal to 0. And I get negative normal force in section 3 and 3 minus 6 kips is equal to 0. Or in other words, n sub 3 is equal to negative 6 kips. I will draw that on my diagram here. That's negative 6 kips. So here is my normal force diagram for this assembly here. And again, sign is very important. If we start calculating the change in length of this column, we notice that this first section and the second section are positive. That means they're going to be elongating. This section here, section 3, it's in compression, so it's going to be shortening. If you don't get the signs right, then you might not get that canceling out action that you would if you follow the sign convention. So one shortcut that I like to explain to people so you can check your work, or if you can explain it adequately on the homework or on the exam, I'll let you draw your diagrams this way as long as you can explain it so I can recreate it, is that as we go from left to right across this assembly, anytime that I have an externally applied axial force pointed to the left, it makes my diagram jump up the magnitude of that force. Anytime I have an externally applied axial load pointed to the right, it makes my diagram jump down the magnitude of that axial force. So as we started at 0 and we end at 0, we're doing that method. And so here I start at 0, I have 6 kips pointed to the left, I jump up 6 kips. No loads are applied until I get to this discontinuity here. And here I have 2 kips plus 2 kips, which is 4 kips pointed to the left. So I jump up 4 from 6 to 10. Here I'm at 10. I have 16 kips pointing to the right, so I go from positive 10 minus 16 to negative 6. I go all the way to this point right here. I have 6 kips pointed to the left, so I jump up from negative 6 plus 6, gets me back to 0. So that tells me that I did this problem correctly. All right, so that's the most common type of loading that you're going to see in this class is discretely applied loads at nodes right here. And so this methodology, the free body diagram, section cuts, equilibrium, it's the rigorous method. It takes the most amount of time, but you have the least likelihood of making mistakes. Then you can go back and check your work using those rules that I just explained. All right, so that's the most common. One example of a constant normal force that often gets done incorrectly is a diagram just like this where it might throw you off because we see this column right here has a varying cross-sectional area. All right, we have a constant, we have 10 kilonewtons pointed to the left at this left support, 10 kilonewtons pointed to the right at that support, so it's in equilibrium. But people think this problem is a lot more complex just because this cross-sectional area is changing. So it's absolutely true that this is going to be more complex in terms of a stress or a deflection calculation, because if you remember, our normal stress calculation is N divided by A. Either of these could be a function of X. Either the normal force could change as a function of X or the area could change as a function of X. All right, but in this case, we don't care about the stress. All that we're looking at is the internal normal force, so the area actually doesn't make any difference at all. The deflection calculation is the integral from 0 to L of the internal normal force as a function of x dx divided by a of x times e. Again, a of x is in that problem, but we're not talking about deflection yet. We're just talking about the internal normal force. So all that you need to do for the internal normal force is make a section cut and figure out whether or not it varies with the distance x. So here, I can make a section cut here or a section cut here. I can make a section cut anywhere in between the left end of the column and the right end of the column, and I'll get the exact same value for the internal normal force. So my free body diagram might look something like this. Here's my section cut. Here's my internal normal force. And we have our externally applied load of 10 kilonewtons here at the left. If I sum the forces in the x direction equal to 0, I get negative 10 kilonewtons plus the internal normal force equals 0. Or in other words, the internal normal force equals positive 10 kilonewtons. And it's not a function of x. It doesn't matter where we make that section cut. It's always going to be the same exact value of n. And so here, it is simply a constant positive 10 kilonewtons the entire length of that column. Don't get caught up thinking that the area matters for the internal normal force. It matters for these other calculations, but in terms of the normal force diagram, it's not going to vary at all. So analytically, a simple problem, but again, conceptually, a lot of students will get caught up with that changing cross-sectional area. Don't let that fool you. It's really a simple problem. Okay, these other two types of loadings will get a little bit more complex. Again, this one's a little bit tricky. These require a little bit more analysis, but just following the same process of making a section cut, drawing a free body diagram, and then writing your equilibrium equation, it'll get you through both of these. It's just a little bit more work. So here we have an example. These are both cantilevered columns with a support on just one end. Here we have a uniformly distributed axial load where the axial load here is pointed to the right, but it's uniformly distributed where it's 100 pounds per foot of an axial load. All right, if this column was rotated, 90 degrees clockwise, that axial load pointed down would kind of be like gravity. All right, maybe here it's an acceleration load or something like that. On this example, we still have a distributed load, but it's no longer uniform, it's varying based off this equation. And I forgot to show an x value here, but x is positive. It's 0 at this point, and it's going positive to the right. So here the distributed load is increasing. It starts out at 0, and it increases following this formula 500 times x to the third power, and it's in units of pounds per inch. So we'll get to that last. That's probably the most complex. First, we're going to do the uniformly distributed load. But if we go back to these discrete loads, it's the same exact procedure. What I'm going to do is I'm going to make a section cut. Here I'm going to make it, the distance is going to make a difference. I'm going to make a section cut here at some arbitrary distance x, because we're going to find the internal normal force here is no longer constant like it is here between these two discrete loads or here along the entire length of the member. Here it's going to be a function of the distance. So I'm just going to draw my free body diagram, and I'm going to keep the portion of the column to the left of the section cut. Give myself a little bit of room. Here's my section cut. Here is my internal normal force N, and I still need to draw my uniformly distributed load. It's an axial load. Again, I've drawn it above the member, but ideally it's going to be acting along the longitudinal axis. But here it's uniform, and it's 100 pounds per foot. We still have the same coordinate system, and I'm missing my dimension here, which is x. So just like with beams and transverse loads, we can represent this loading in terms of an area is going to give us the resultant force. In other words, this is a uniformly distributed load, so it has a constant magnitude the entire distance. If I were to plot, if this is what we call a variable w for a distributed load, I have a loading diagram that's just a horizontal line. And so the resultant, or to go from a distributed load into an actual force itself, we see that the units here are pounds per foot. So to get to force or pounds, all that I have to do is multiply by a distance. Right? That distance is going to be the length that the loading is applied on. So the resultant force here, the total resultant force is the area underneath that loading diagram. Here it's constant, so it's just the base, the width, the base times the height, which is W. And the same thing applies for the free body diagram. My resultant force, I'll just call it R, is equal to the area underneath this loading diagram. All right, my loading diagram has a magnitude of 100 pound per feet, and it has a width of x. So my resultant force here is simply equal to 100 pounds per foot times x. And so if I wanted to figure out the relationship between the internal normal force and the resultant, I'm just going to sum the forces in the x direction equal to 0, and I get minus r minus the resultant, because the resultant is pointed to the left, plus the internal normal force N is equal to 0. But I can take r and substitute in the formula for it, because I know it's a function of x. And so I get minus 100 pounds per foot times x plus the internal normal force is equal to 0. And actually, I drew this in the wrong direction. Up here, I had this shown pointing to the right. So let me fix that just really quick. It's the same exact derivation. I just need to change the sign. So I'm sorry, up here, all of these distributed load arrows are pointing to the right. And so I need to change that here. My resultant is pointed to the right because my distributed load is pointing to the right as well. And so when I sum this up, my resultant's pointing to the right is positive. My internal normal force is pointing to the right. It's also positive. Those sum up to 0. Okay, so I apologize for that mistake. All that we changed were the directions of these arrows right here. And so if this is my equation, I can solve, get the internal normal force on one side. And now the internal normal force becomes a function of x. And it's equal to minus 100 times x. And that's going to be in units of pounds, if x is in feet. Okay? And so the units here are going to be pound, as long as x is in feet. And so if that's my function for the internal normal force is a function of x, it's a linear relationship. It's just x to the first power. So if I want to plot that out, I really just need 2 points. 1 point at the beginning, 1 point at the end. Because it's linear, I know I can fit a straight line in between the 2 points. And so at x is equal to 0, at x is equal to 5 are the 2 points that I care about. So here, n at x is equal to 0. This is equal to minus 100 times 0, which equals 0 pounds. The internal normal force at x is equal to 5 feet is going to be equal to minus 100 pounds per foot times 5 feet, which is just minus 500 pounds. Okay, so negative 500 pounds and 0. I get a straight line in between the two. This is minus 500 pounds. And that is my internal normal force as a function of x across the entire length of this column. So think of this as a calculus-based relationship. This internal loading is the integral of this loading diagram right here. Okay? Where, in other words, n is simply the integral of w over the length of the column. So we'll use that same analysis for a more complex distributed loading. Here, instead of a uniformly distributed load, we have a varying distributed load. And so, just like up here, I can draw a diagram of what W looks like. In this case, instead of being a rectangle, we have x to the 1/3 power. So my loading diagram is going to look something like this, where again, at any given point, W is equal to 500 times x to the 1/3, and it's in units of pounds per inch. Okay? So essentially our internal normal force diagram is going to be the integration of this varying distributed load equation, but we can figure that out just based off a section cut, a free body diagram, and our equilibrium equation. So I'm going to make a section cut at x. I'm going to draw my free body diagram. I'm going to keep the portion of that column to the left of that section cut. We get our section cut right here. My internal normal force, N. Again, the geometry of this section cut is x long. And then we need to draw our distributed load here. And I'm trying to show it with the magnitude increasing as I go to the right. But again, this loading diagram looks like this, with W being equal to 500 times x to the 1/3 pounds per inch. And so if I want to figure out the resultant force, the resultant force will be equal to the area underneath this loading curve, this distributed loading curve. So I need to find the area underneath that curve. It's not just a rectangle at this point, so we can't just rely on basic geometry, base times height, to figure it out. Here we need to use an integral to calculate the area underneath that curve. And so if I were to solve for r, R is equal to the integral from 0 to x. This is x is equal to 0. This is x is equal to x right here. So the integral from 0 to x of 500 times x to the 1/3 power. And we're taking that integral with respect to x. And so I can solve for this. And I will get 1,500 fourths, which is I think 375, times x to the 4/3. In other words, 375 times x to the 4/3 power. That's what r is equal to. R is a function of x. And if I were to sum my forces in the x direction equal to 0, I would get positive r because this resultant is pointed to the right, plus the internal normal force n is equal to 0. Or in other words, the internal normal force is a function of x is equal to minus r, which is also a function of x, which we solved for up here. So it's equal to minus 375 times x to the 4/3. So we care about two different locations here. Well, actually, because this is no longer a linear relationship, we care about probably a couple more points to plot it out accurately. But we definitely care about the internal normal force at x is equal to 0. We definitely care about the internal normal force at x is equal to 48 inches, which is the end of the beam. Maybe we also care about the internal normal force at maybe half the distance, which is 24 inches. So let's calculate each of those. The internal normal force at x is equal to 0 will simply be 0 pounds. We're also going to calculate the internal normal force at x is equal to 24 inches. And the internal normal force at x is equal to 48 inches. All right, I have those numbers tabulated here. At 48 inches, it's 65,416 pounds, or 65.4 kips. And that'll be negative. And at 24 inches, we have negative 10.3 kips. All right, so if we were to plot those points, again, we have 0, 0. At 48 inches, we have negative 65.4. We already showed this vertical axis in units of kips. And at 24 inches, we have a value of negative 10.3. All right, so we see that we have a parabolic distribution. Missed that last point a little bit. We'll just fix that. And that shape makes sense because here the power of x is above 1, so it should be parabolic. And so here's what the internal normal force diagram is going to look like across the length of the beam, the length of the column. A lot of students will just plug in the value of x here at the end to our distributed load equation. But again, always check the units on your final answer. Here we went from pounds per inch for W, and we multiplied it by this distance x. So we went from pounds per inch times inch was pounds, so we ended up in force. If you were to just plug in a value here of x is equal to 48 inches, right, that's just going to end up with the same units, pounds per inch. That's what W is in units of, it's in pounds per inch. So it can't be a force, it's the intensity of a force at a given point, but it's not the actual force itself. So dimensionality is a really important way to check your results here. Okay? So 4 different types of common loadings. Discrete loadings is the most common. Section cuts, free body diagram, equilibrium equation, the sign convention being very critical. But other than that, it's a bit boring of a process, but if you do it the rigorous method, you're going to get the right answer. Constant internal normal force, don't be fooled by changing cross-sectional area. That doesn't affect the normal force at all. Uniformly distributed load, there's some Geometric integration, just solving for the area underneath a simple loading curve. And then a varying distributed loading gets a little bit more complex where you have to use actual integration to solve for the internal normal force.